Okay, it's a great pleasure to be here, and I'd like to congratulate the three near birthdays. This meeting is being recorded. Got it. So, what I'd like to talk about today, maybe it's not the main theme of the meeting, but I think it's interesting, and it involves quantum theory and quantization. It's based on Fourier analysis. And in classical Fourier analysis, we have two types of multiplication, the ordinary pointwise multiplication and convolution. They're exchanged by Fourier transform, and they lead to the central limit theorem, which is the standard elementary result in probability theory. There are many entropy inequalities, uncertainty principles that are basic in quantum theory, and measures of complexity. And there's a new subject I'll talk about at the end of my talk called higher Fourier analysis, which also has been very popular over the last 25 years and extremely important in combinatorics and number theory. And what I'm going to talk about today is a quantum analog of these same things in a discrete quantum theory, having to do with qubits and qdits, which are two or d-dimensional quantum excitations of particles. So I'd just like to comment first that I've had a very happy career. Most people my age are retired, but I'm happy to be able to do some research with extraordinary students, postdoctoral fellows, collaborators, including Jonathan, and I'm so sorry Jonathan can't be here today, but I spent yesterday afternoon with him. And took a photo. Normally, I like to put a lot of photos in my talks, but I was just in Europe a couple of days ago and had to come here without being able to search my home for many photos of Jonathan that I have from the time he was a student. So I took one yesterday, and this is his photo of Eva and Jonathan. But I've become used to having students from the United States and Europe, and now so many come from China. So I'd like to introduce a couple of my friends who I'll talk about our joint work today. Chengwei Liu came as a postdoctoral fellow in 2015 as a student of Von Jones, and now he's a professor at Tsinghua University in China and executive director of the new institute BIMSA, where they're hiring many mathematicians, and where last week there was a wonderful conference on mathematical physics. I have a present set of collaborators I'll talk about central to this. Kaifeng Bu just finished as a postdoctoral fellow, and he's going to be this fall at Ohio State in the math department. And there's a student, Weichen Gu, who spent some time at Harvard as a visiting student, just finished a PhD at the University of New Hampshire, and he's going to be Kaifeng's postdoctoral fellow in the fall. So I had many other collaborators recently, and here are just some pictures to indicate that there was a large group of people coming through Cambridge that I've interacted with. I'm going to talk about this picture language for quantum information, which started in work in, the first paper was published in 2017 with Chengwei. And it has to do, in the simplest case, with a single particle, which is a d by t qubit matrix. For d equals 2, it's called qubit to describe a fermion. So in these pictures, they're represented as an input and output with vertical multiplication. And this is a transformation T on this d-dimensional, finite dimensional Hilbert space. multiplication is vertical, t times s, t below s on top. And the adjoint, Hermitian adjoint, is got by inverting the picture, reflecting vertically. So a simple example is an annotated temporally Lieb algebra. Here, temporally Lieb has normally n inputs and n outputs. I've drawn the simplest case of 2. And I could take the example of T being an annotated diagram where the label K is an element of the cyclic group ZD. So that represents the D states of the qubit. And the group is additive, so K times L is K plus L. The adjoint reverses K. It's called charge conjugation. So it takes K to minus K or L to minus L. So here, with this choice of T and S, we can look at T times S or S times T, and it just has to do with the vertical order of the labels. And these are related in this algebra by what we call para-isotopy. So you cannot just isotopy the charges, but if you exchange their order, you pick up a phase omega, which is a d-th root of unity. That's where D comes in. So T times S is omega to the KL S times T. For the case D equals 2, that's called fermions. And the case D greater than 2 in physics, it's called parafermion. So the trace is given by those pictures in planar algebra where you take the input lines and connect them to the outputs without crossing. And there's a value assigned to a circle, which is 0 if K is non-zero mod D, or square root of D, which is a special case for quantum information in case K is 0 mod D. This trace with this choice of the circle is positive, namely if you take the trace of any T star T, it's greater than or equal to 0. And this is a special case of Jones index theorem, who showed that there are certain values of the circle which give positivity for the temporally algebra. So using the positivity of the trace, it's also trace of T times S is trace of S times T, we can define an inner product, which is 1 over the dimension times the trace of T star S. So the simplest example in detail is to look at the matrix units in this algebra. And here is the picture of the matrix unit EKL. They're orthogonal, in fact, orthonormal in this inner product. And they form a d squared dimensional basis for the finite dimensional space. So to connect to Dirac notation, this is the basis element K, and the matrix unit is the map from L to K. And the resolution of the identity then is given by the sum of the diagonal elements of the matrix units. Now, what is the Fourier transform on these matrices? There are many Fourier transforms of operators that are studied, and the particular one comes out of the old work of Acciano, where you take the inputs and outputs and cyclically permute them by 1. So for 2 inputs and 2 outputs, the Fourier transform of T is the picture on the right where the upper right input is converted to an output and the lower left output to an input. So it still is a transformation from 2 points to 2 points, and it's actually inner product preserving. It's a unitary with respect to the inner product. And the way to see that is just to write down the diagram for the inner product of the Fourier transform of T with the Fourier transform of S. And it's the picture on the right where the Fourier transform of T inverts it. The adjoint inverts it, and the Fourier transform takes the lines around. And now if we take the trace of the picture on the right, we take the input on the far left and the output on the far left and connect them. We can isotopy them into a short line connecting reflected T with S. And then it's clear if we take the second line and connect it to make the trace, that the trace of the 2 sides are equal, and this theorem is proved. So I claim this Fourier transform actually generalizes the standard Fourier transform on the group ZD. But that generalization is it agrees with the standard Fourier transform for diagonal matrices. So if we take the diagonal matrix units, E sub kk, and take their Fourier transform, it's just the sum over this root omega to the ku times EU up to a normalization. So how do you, here I wrote it out in terms of pictures, the same equation as the top one. Now, I don't want to go through the proof, but I wanted to show you it's a very elementary calculation using the things that I've already said. And one additional relation, which is the Gaussian braid relation, how to transfer the label on a cap from the left to the right. It involves a Gaussian factor, zeta to the k squared, where zeta is the square root of this omega, the dth root of 1. So zeta is a 2d root. And so the proof is given in terms of these pictures of the special Fourier transform on the diagonal matrices. In the first identity, we use the braid relation to transfer the charge. I think of these labels as charges on the bottom from left to right, and it gives a Gaussian factor, and then take the Fourier transform, which rotates the inputs and outputs. And then I can use the para-isotopy to reverse the order of the charges, and that will just produce a factor omega to the k squared, which changes zeta to the k squared to zeta to the minus k squared. And now if I insert the resolution of the identity, we're almost finished. We just use the braid relation to go and take the k. Well, we can translate the sum for the resolution of the identity and then take the k on the right over to the left, and we get a factor given the Fourier transform. So this is the simple proof that the Fourier transform is correct on diagonal matrices. Now, there are special matrices that come into quantum information, and they're the so-called Pauli unitaries, which generalize the generators of SU2, the 2x2 matrices for d equals 2. And they're defined on the basis Z has the eigenbasis, the standard basis, just with eigenvalue omega to the k, and X raises the label by 1, mod D. So they're the sigma X and sigma Z, which are generators of SU2 in the case D equals 2. And diagrammatically, the X and Z are represented by these two diagrams, where one labels k equals, charge k equals 1, and Z is interpolated where the charges are at the same vertical level. And that's interpolation. If the order of multiplication of k and L were reversed, there'd be a factor omega to the KL. And the interpolation takes the square root of that phase when the two are on the same level. So Z times X is omega X times Z, and the XZ and this constant zeta generate what's called the Pauli group. So I claim that the Fourier transform of the matrix units are just the generators of the Pauli group. That the Fourier transform of the matrix unit EKL is just Z to the K times X to the K minus L. And that's another simple computation that I wrote here, but I won't go through. So for n particles, or n qubits, you take the tensor product of this construction that I just outlined, the n-fold tensor product of CD, and that's the Hilbert space of n quantum qubits. So it's generated by the corresponding tensor products, where you take a Z and X, there are D squared of them in each tensor product, and take some powers, and those are the generators of the Pauli group for n qubits. So that was my introduction to quantum theory of n d state particles. For d equals 2, that's what's realized in the laboratory for people who are trying to build a quantum computer. At Harvard, they have 1,000 qubits in the laboratory already. And they're looking to simulate d equals 3, which has many properties that are nice over the d equals 2 case. And so that's why the general d case is interesting, and it's also interesting mathematically. So now I'd like to make a transition back to classical probability theory and explain the central limit theorem. Everybody here probably teaches it in a first course in analysis, but let me just review the basic facts. I start with a function of a single variable x, real variable, positive function with integral 1. That's a distribution, rho. Its first moment I'm assuming to be 0, and the second moment 1. That gives us the normalization. The Fourier transform in probability theory is called characteristic function, and it's the expectation or integral of rho times e to the itx. Now, one takes in probability capital N independent copies with, say, the same probability distribution rho. And the sum of the n copies will have mean 0, since each mean is 0, and the variance capital N. So if we want to calculate z, the kth moment of z in the product distribution given by the rows in each variable, it's just the integral of z to the kth moment in some distribution rho n, which is set the n-fold convolution of the original one. And that's how convolution comes in. And we can consider the Fourier transform of the distribution rho n as phi sub n. That's the Fourier transform of the n-fold convolution. Now, the central limit theorem normalizes this z to take its variance back to 1 by dividing by square root of n. And if we compute the characteristic function, then the Fourier transform of rho n, because Fourier transform of convolution is a product, is just the nth power of the Fourier transform of the original distribution, and it's scaled by t over square root of n. And if you just make a Taylor series expansion of phi in t, it's normalized so that its integral is 1, so phi of 0 is 1. The first moment is 0. The second moment is this t squared over 2n with a minus sign. And the third moment gives an error, t cubed. And so for large n, as capital N goes to infinity, it converges to a Gaussian, which is just the formula for an exponential. And if we take the inverse Fourier transform, we get the Gaussian distribution, which is the central limit theorem. So what is the analog of this classical distribution rho in quantum theory? It's called a discrete quantum state or a density matrix, namely a matrix with positive eigenvalues and trace 1. So is there a convolution? This was discovered by Kaifeng and Weichen in a joint paper. And here's the formula for the quantum convolution. You first take two states, rho and sigma, which are each positive matrices with trace 1, and take their tensor product. And then you twist by some unitary v, which is appropriately chosen, and take a partial trace on the second factor. This has the property that it takes positive rho and sigma into positive rho times sigma, which is denoted with this box, and will produce an output with trace 1 because it's just given by the twisted unitary of the tensor product. And so it takes a state to a state, and in fact, the trace is just the product of the traces. So what is the choice of this unitary V? Well, there are different choices, and I'll give a particular one. If we choose S and T to be elements of ZD, which have squares summing to 1 mod D. So for example, if we take S or T to be of this form, then you can define V to be a rotation in the 1-qubit space and take the tensor product in the n-qubit space. And that leads to a quantum central limit theorem. Namely, if rho is mean zero, I have to define that, but let me skip over the definition of mean zero. Then multiple convolution given by this formula that I just showed converges exponentially fast to a quantum Gaussian. And we call it the mean state M of rho. And the quantum Gaussian in quantum information is called a stabilizer state. I'll explain later what is a stabilizer state. And the state that you get as a limit, this quantum Gaussian, the normal distribution in quantum theory, is the closest stabilizer to rho measured by relative entropy. Namely, if you have a state, rho, and the set of stabilizers, which I haven't told you yet what they are, and look for the closest point in the stabilizers to the original rho with mean zero, that's what this multiple convolution converges to. And the relative entropy is the trace of rho log mo minus the trace of rho log m of rho. And it's minimized by this limit. So in addition, there's something like the second law of thermodynamics, where if you take the von Neumann entropy, S of rho, which is minus the trace of rho log rho, then each convolution increases the entropy. And if the original state has mean zero, it increases to the entropy of the limit. So now I should explain what is a stabilizer. First, we ask, what is a stabilizer group? This is an abelian subgroup of the Pauli group. Remember, the Pauli group is the group generated by the Fourier transform matrices of the unit matrices. The Pauli group is generated by Z, X, and this square root of omega. And we take a maximal abelian subgroup of the Pauli group with generators G sub J. Now they commute, so they can be simultaneously diagonalized. And we can normalize it so they all have eigenvalue 1, and there's a vector which is called a pure stabilizer vector, which is the invariant vector under all the generators of the group. And a stabilizer state is just the rank 1 projection onto that vector. And that's a pure stabilizer state, and a general stabilizer state is a convex linear combination of stabilizer states. So in physics, Bravi introduced the notation, maybe Bravi and Kitaev, magic, to denote something that's not a stabilizer state. So what are some examples of stabilizers? Stabilizers, in quantum theory, a great deal of talk is about entanglement. But magic is different from entanglement. Because the simplest example of a stabilizer is the so-called Bell state, which is given in the tensor product n equals 2 of two qubits. So for a qubit, the so-called Bell state is the state 0, 0 plus 1, 1 normalized. And the stabilizer group is generated by x1, x2, and z1, z2, where the subscripts denote on which element of the tensor product the operator acts. So for instance, if you apply x1, x2 to 0, 0, you have the state 1, 1. And if you apply x1, x2 to 1, 1, you have the state 0, 0. So the Bell state is invariant under x1, x2. And if you apply z1, z2 to 0, 0, you get 0, 0. If you apply z1, z2 to 1, 1, you get minus 1 squared, which is 1. And so it's also invariant under that. So if I should have put this before, xj acts in the jth place as x. Bell state is maximally entangled, but it's a stabilizer. And there's another Bell state if we take the stabilizer group with minus x1, x2, z1, z2. Then we get 0, 0, minus 1, 1. And for n qubits, Greenberger, Horn, and Zeilinger introduced the analogous Bell state. It's called GHZ, and it's just the sum of the state k, 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 k normalized. So here the stabilizer is the product of x's and a pair of z's, z1, z2 inverse, z1, z3 inverse, and so on. So another example of an n-qubit state, which is a stabilizer, is called max, and that's the sum of the tensor product where the total charge, k1 up through kn, is 0 mod d. These two states are related to one another by Fourier transform. Yes? Oh, if what you can do is this quantum Fourier transform that on the product of 0, 0, 0 produces the max state. So if you look at it that way, it's a one-off operation. And here's the corresponding stabilizer group for the max state. It's z and x are interchanged by Fourier transformation. So here's a simple example for a single qubit. Another example, and a magic state, which is not a stabilizer, is a sum with the square root of zeta, in the case d equals 2. So what are some other properties of these quantum states? Well, the convolution of two stabilizer states is a stabilizer. And I told you that the convergence to the mean is exponentially fast, and we call this rate of convergence G the magic gap, because it, by multiple convolution, removes magic. But it's very tempting to think that the magic gap is related to the spectrum of some transformation. We don't know that it is, but we'd like to find that transformation. Because in graph theory, there's an analogous gap called the Cheeger constant for large matrices, which is given by the spectral gap of the adjacency matrix. And in quantum field theory, the gap in the Hamiltonian plays a very essential role. So it would be very beautiful to find an interpretation of this magic gap in terms of a transformation in which the gap is the gap in the spectrum. So that's a conjecture. Now, there's a theorem of Gottesman and Nil, proved in 1998, that you don't get quantum advantage, that any computation that can be performed in terms of these, well, I didn't define Clifford yet, but there's simple inputs and gates constructed from these Pauli operators can be simulated in polynomial time with respect to the size of the transformation on a classical computer. So entanglement does not help to get a quantum advantage, but you need magic. So we have a lot of work on these things. I switched from studying quantum field theory to quantum information around 2015 when Cheng-Wei came as my postdoctoral fellow. And since then, we started what we call the Picture Language Project. And if you want to see the papers coming out of this group, then we have a website called MathPicture, FAS Harvard.edu. And we have a list of papers there. And already, since we started this, we have well over 100 papers. So there are a lot of things that I'm just skimming over, but if you want to find the details, this is the place to go and you can see all the papers. So I'd like to end up by just saying something about the so-called Clifford hierarchy. This is a concept in quantum computation. And it is a hierarchy of sets C. The lowest set, C1, is the Pauli group. That's the group generated by Z, X, and this constant zeta. And then the hierarchy is defined inductively for K greater than 1. It's the set of unitaries that take a Pauli matrix that's an element P in C1 into the CK. So conjugation by U maps a Pauli matrix. If we take K equals 2, that's called Clifford unitaries. And the hierarchy is a hierarchy of complexity of quantum information, complexity of quantum gates, which is based on this definition. And in classical theory, there's this subject, I mentioned higher order Fourier analysis, where in ordinary Fourier analysis, one pairs a function with the exponential of a linear function. And in higher order Fourier analysis, one pairs a function classically with the exponential of a polynomial. And a polynomial of degree k, it's higher Fourier analysis of degree k. And there's a set of analytic tools that were introduced in the late 1990s, first by Timothy Gowers and then taken up by Terry Tao, Ben Green, Tamara Ziegler, and many others, in which they found that this notion of higher order Fourier analysis was very useful in combinatorics and number theory. And this is based on having a discrete derivative where you take, say, in the quantum theory, we would take a unitary U and translate it. Well, W, this translation, is just one of the Pauli operators, one of the elements in the Pauli group. And classically, you would just take Z or X, and then it would be an ordinary type of translation. And here we have a translation in phase space where we think of Z and X as generating a quantum phase space. And then take the inverse. So we're taking some discrete derivative in the exponent. So if you take U to be the exponential classically of a polynomial of degree k, this derivative would be the exponential of a polynomial of degree k minus 1. So we can use this Pauli operator to define a discrete derivative in the quantum theory. And the conjecture is that the Clifford hierarchy is quantified by quantum uniformity. Now, what is uniformity? That's a quantum version of the uniformity norms, well, the uniformity measures. And what we're investigating now, here is one measure. In the case of k equals 2 and 3, we know it's a norm. We don't know it's a norm for k greater than 3, but it's probably not necessary that it be a norm. And it's got by taking the k-fold derivative of a matrix A and taking its trace, normalized trace, and its expectation over the different translates. And then there's a overlap, which is a related measure, which is just how far a particular unitary is from the set of unitaries in Ck minus 1. And it's known that the norm or measure for a unitary with small q is less than the one for the big Q. That's a famous inequality in the classical theory, which led to the results in number theory. And it's the inverse norm conjecture of Gowers is that there's an inequality in the reverse direction, but this is only proved in a number of very special cases, classically. And quantum theory, we don't at this point know this inequality, but we think that this is also going to be quantitatively useful in quantum information. So I think there's much more to discover in quantum higher order Fourier analysis. And I'd just like to end my talk there. Thank you.